Testing. Okay. Okay. That's all right. Oh. I recall the last time you were here, you were discussing group structures. And we did a couple of examples, and I talked about moment charges. Okay. So let's talk about polarity of bonds and as it relates to electronegativity of the atoms. Now, I don't think I've defined electronegativity before, at least not in this course, so let me do so now. By definition, electronegativity is a measure of the ability to of an atom to attract shared electrons to itself. All right. And some electronegativity values were determined by a guy by the name of Linus Pauling. He used some thermodynamic data, including ionization. Oh, I got to share my screen. I apologize to you guys out there in Zoom. Okay, now you should see what we're all seeing. Okay, so as I was saying, electronegativity is defined as a measure of the ability of an electron or of an atom to attract shared electrons to itself. All right, and I was just saying that a guy by the name of Linus Pauling, a Nobel Prize winner, in fact, he won 2 Nobel Prizes, one for chemistry and the other one for physics, if I remember correctly. No, for peace, I think. Anyway, he basically combined in some way thermodynamic data such as ionization energy and electron affinity. And he came up with a scale, a 4-point scale. And basically, based on where that particular element ends up on the scale, you can tell whether or not that particular element is more electronegative or less electronegative than another element, right? So basically, as stated here, if you have an atom bonded to another atom in a molecule, then basically the one that's more electronegative will have a stronger attraction for the shared electrons, right? That is shared between the 2 atoms. And as you can see here, there is a trend or trends in the periodic table with respect to how the electronegativity of an atom varies as you go from left to right of any period. The electronegativity increases, and as you go from bottom to top of any group, the electronegativity also increases, all right? And I don't think there are any exceptions to those trends, all right? And there's a table in the handout that is posted in Canvas, which you'll have access to. This basically gives you a summary of all the, well, not all, I don't think they have all of them, but most of the electronegativity values of different elements in the periodic table. And if you look at the numbers here, as I said before, it's a 4-point scale. So the most electronegative element is fluorine, 4, right? And then you have others of different values. Metals typically have very low electronegativity values, and over here, the non-metals, they tend to have high values, all right? So that's as far as electronegativity is concerned, and that's important. Yes, sir?
Why is helium altered?
I'm sorry?
Why is helium altered?
Why is helium what?
Not altered.
Oh, because it has no tendency. Helium is a group 8 element. You don't see group 8 elements listed there. That's because they have no tendency to either attract or form bonds.
Gases.
Yeah, the noble gases, exactly. Because they're stable by themselves. So you don't see in this list here group 8 elements indicated. All right. Okay. So let's see what it says here. All right, so the 4 most electronegative elements in the periodic table are these right here: nitrogen, oxygen, fluorine, and chlorine. And of these 4, fluorine is the most electronegative. All right. So referring to the periodic table, and nothing else. Let's see if we can order these series of atoms or elements in order of increasing electronegativity value. Let me see if this is working. Okay, this is working. Okay. So remember now, the trend is going left to right, the electronegativity increases, going from bottom to top of any group, the electronegativity increases. So the first series here is chlorine, magnesium, and silicon. So let's see, magnesium is there, chlorine is there, silicon is there. Okay, they're all in the same period, right? So which of these would be, let me see, it says increasing. Okay, so we're starting from the lowest to the highest. Which of these would have the lowest?
Magnesium,
Magnesium followed by?
silica,
Followed by?
chlorine.
Exactly. So that's the answer for A. What about B? B is arsenic, nitrogen, and antimony. Where's that one? Okay, they're the same groups. All right, so of these three, which would you expect to have the lowest?
Antimony,
Antimony would indeed have the lowest, followed by
arsenic,
arsenic, and then of course nitrogen. All right, and then we get to arsenic, selenium, and antimony. Okay, so what do we have here? Okay, so arsenic and selenium are in the same period, but arsenic and antimony are in the same group, and selenium is to the left, I'm sorry, to the right of arsenic. Okay, so with that said, of these three, which would you expect to have the lowest?
antimony,
Antimony would be the lowest in terms of electronegativity,
arsenic,
and then arsenic, and then selenium, right? So that's basically how that is done. All right. Okay. Any questions? Any question about it? Any questions? All right, continuing. So let's talk about how electronegativity affects bonding, right? In terms of bond time, right? So the first thing we're going to talk about is the simplest situation where if you have two identical atoms, like two chlorines or two oxygens, right? Bonded to each other. Obviously, both atoms will have the same electronegativity values because they're identical. So therefore, what you find is that the electrons will be equally shared between those two atoms, right? So we say that that bond is what we call a non-polar covalent bond because the electrons that are shared between those two atoms that are identical will be shared evenly, all right? Now, if the electronegativity values of two atoms differ significantly, so we're talking about different atoms, right? So you could be talking about, let's say, hydrogen bonded to oxygen, or let's say sulfur bonded to chlorine. In those situations where you have a significant difference in their electronegativity, we say that that bond is a polar covalent bond. So what that means basically is that the electrons would be, on average, be closer to the more electronegative atom compared to the other atom. So there's a separation of charge, which I'm going to show later on. And then if you have a situation where the difference is very large in terms of electronegativity, then we say that that's an ionic bond. Now, basically what that means is that you have a complete transfer of the electrons from the metal, which is typically the case, to the non-metal, right? So the question now becomes, how do we establish a criteria for determining the different types of bonds? And different people have different ideas. I'm going to use the one I'm about to show you shortly. But before I do that, let me just show you this diagram here, which basically gives you some examples and where they lie on the scale here. Now, down here is a scale which represents the difference in electronegativity of the two atoms involved, right? So if you have, let's say, carbon to hydrogen, that is essentially, even though they're two different atoms and they have two different electronegativity values, the difference is so close that for all intents and purposes, in most cases, the carbon to hydrogen bond is considered to be nonpolar. And then when you get to above 0.4, right, like NH or CO, right, those bonds are considered to be polar. And then when you get to higher, like up here, the bond is considered to be ionic, right? In fact, that's the answer to this question right here. It says the CFF bonds are so polar that we call the bonds ionic, because basically what that represents is a complete transfer of electrons from the metal to the non-metal, right? It says there are no sharp cutoff between ionic and covalent bonds, right? So the criteria that we're going to look at to make a distinction between those bonds is not a hard and fast kind of thing, but we're going to basically use that in order to establish the different types of bonds. So this is the criteria for determining whether or not a bond is nonpolar or covalent. If the difference in the electronegativity values is between 0 and 0.4, right? For most intents and purposes, those bonds are considered to be nonpolar, right? And some examples are shown here. Obviously, if you have two identical atoms, as I said before, that bond would be obviously nonpolar. But if you have something like a chlorine to bromine bond, where the difference in the electronegativity values is 0.2, then we say that that bond is nonpolar covalent. And the same is true for the hydrogen to silicon bond, same thing, right? So if the difference in electronegativity is between 0.0 to 0.4, then we basically can assume that that bond will be nonpolar covalent. Now, when it comes to polar covalent, the difference would have to be from 0.5 to 1.7, right? If we have such a difference between 0.5 to 1.7, then that bond is essentially a polar covalent bond, such as the oxygen to chlorine, where the difference is 0.5, the chlorine to carbon, where the difference is 0.5, and the oxygen to sulfur, where the difference is 1.0. All right, so these are all polar covalent bonds because the differences in their electronegativities lie within this range from 0.5 to 1.7. And then pretty much anything after and including 1.8, if you have a difference between the two atoms involved, then those bonds are essentially ionic. And these are just some examples. And this is typically a bond between a metal and a non-metal, even though there are a few instances where the bond between the metal and non-metal or the difference can be less than 1.8, but for most intents and purposes, the differences will be greater than 1.8 or equal to 1.8. And we see some examples here, all right? Okay, so just to give you a picture of what we're talking about when we're talking about the difference between a polar covalent bond and a non-polar covalent bond, what you're looking at here is the situation where you have hydrogen bonded to another hydrogen atom. The electrons that are shared between them will be equally shared. So therefore, you won't have any lack of symmetry in terms of how the electrons are shared between the two atoms. So therefore, we say that this bond is non-polar covalent. Now, if hydrogen is bonded to something electronegative like chlorine, then what will happen is that the shared electrons, on average, will spend more time around the chlorine than the hydrogen. So therefore, you will notice that the distribution of the shared electrons, this is their orbital, so to speak, will be such that the bulk of the density will be around the chlorine, right? And this is called an electrostatic map, which shows you, it's a modeling technique that is used to basically highlight, whether or not a bond is polar. Red usually means that the electron density is high in that region, and blue means that the electron density is low. So basically, as you can see in this representation here, the electrons on average will be closer to the chlorine compared to the hydrogen, all right? Okay, so there's another way of representing the polarity of a bond, and that's what you're looking at here. This is hydrogen bonded to chlorine, and we put this symbol here. Now that's delta, the Greek letter delta, and in this context, it basically represents partial. So what we're saying here is that we have a partial negative charge on the chlorine and a partial positive charge of equal magnitude on the hydrogen, right? So that's basically another way of representing the fact that you have a shift in the shared electrons towards the chlorine. And therefore, as a result, we end up with a separation of charge. Not a full charge, not a full plus or full minus, but a partial negative or partial plus charge. And then there's yet another representation which we can use to measure or to show the direction of what we call the dipole moment. I think I'm going to give you a definition of that shortly, right? But basically, the dipole moment is a vector quantity which shows you the direction of the separation of a charge. And the convention is that to represent the dipole moment, we use this arrow here, right, which shows you the direction of the dipole, which is from the positive end of the bond to the negative end, right? So the way we represent the direction of the dipole is we use an arrow with a cross at the tail of it, right? That's the convention that is used to represent the dipole within a bond and also within a molecule. We're going to talk about how we determine whether or not a molecule is polar, all right? But now we're just talking about the polarity of bonds. Okay, so let's look at this example. Now, for us to answer this question, I wish I could do a double screen thing. We need the table. What do you want? What am I gonna do? Let me try something here. This is the table we're gonna need. Let me see if this will work. Smaller, oops, no. What?
Will we be given that chart?
Oh, yeah, oh, yeah. That is in the same packet that is in Canvas. Let's see, this is working. Right, it's not. Okay, how am I gonna do this? Okay, maybe somebody can put it up on their device, and let me know what the numbers are. Because we need the numbers for the, electronegativity values. I was trying to copy and paste it to this page, but with very little success. Okay, so I need your help. Let me just write down the numbers here because I'm just gonna look at these elements here. What's the value for bromine? 2.8. Okay, what's the value for chlorine? 3.2. 3.0. 3.0, okay. And for fluorine, I know it's 4.0. And hydrogen, what's the value for hydrogen? 2.1. And okay, we got fluorine already. Iodine, what's the value for iodine? 2.5. Okay, so I think I got all the atoms and their values. Okay, so what we need to do is to order these in terms of increasing polarity, right? So again, from the lowest to the highest. So what we have to do is look at the differences in their electronegativity values, all right? So for bromine and chlorine, the difference is 2.8 minus 3, so that's 1.8. So I'm just going to write down the differences here. Difference in electronegative values, right? So 1.8, no, what do I say? It's 0.2, my bad. Bromine and chlorine, right? 3.0, okay, 0.2. Chlorine and chlorine, that will be 0. Chlorine and fluorine, okay, so chlorine and fluorine, so that's 4 minus 3, so that's 1.0. Hydrogen and chlorine, so that's 3.0 minus 2.1, so that's 0.9. And then iodine and chlorine, 2.5, 3.0, so that's 0.5. So these are the differences. So we just go according to the lowest to the highest. So basically, the chlorine to chlorine bond would be the least polar, followed by the bromine to chlorine bond, followed by the iodine to chlorine bond. Iodine to chlorine bond, followed by no, wait a minute. Oh, yeah, okay, iodine to chlorine, then hydrogen to chlorine, and then chlorine to chlorine, and that would be it. Right? That's how you determine the order of polarity. All right. Okay, any question about it? Okay, let's talk about certain molecules, going back to Lewis structures, that don't follow the octet rule. I think I made mention of the fact that I don't think I made mention of that. So let me just talk about that now. So there are certain situations where when you're putting together the Lewis structure, that the central atom will not have 8 electrons on its outer shell, right? And in some cases, for example, where you end up with a total number of valence electrons that is odd, right? Which means that there will be at least 1 unpaired electron, right? So therefore, we call these structures free radicals. Free radicals are basically structures that have one unpaired electron, all right? In other situations, you might have a situation where the central atom would have less than 8 electrons on its outer shell. And this is usually compounds of boron, beryllium, and aluminum, right? And they are very reactive because what they try to do is find electron pairs so that they can complete their octet. And by the way, that is true also for free radicals. Free radicals are also very active. They try to basically gain electrons so that they end up with all their electrons paired. And then we have some compounds that can have more than 8 electrons on its outer shell because they have what is called expanded valence shells, right? So that will take place in certain situations where the elements are from period 3 and below in the periodic table, 3, 4, 5, 6, and so on, all right? So that's what happens in some of these cases, all right? So these are the situations where the central atom will not have 8 electrons on its outer shell, right? So as stated here, and this is in relation to this last statement right here, the central atom can have an expanded valence if it is in the 3rd period or lower, as I said before, right? So atoms like sulfur, chlorine, phosphorus, etc., can actually do this, all right? Okay, so with that in mind, let's see if we can do the Lewis structures for these molecules and ions. The first of which is DRF5, all right? So, as before, what we do is we count up the valence electrons. So bromine will contribute 7, fluorine will contribute 7 times 5. That gives you 5, 7, 35. And then 35 plus 7 gives you 42 electrons, which will equal to 21 pairs. All right. So we put the bromine in the middle, surrounded with the fluorines. And again, we're not concerned with the actual 3-dimensional shape of the molecule. So it doesn't matter how you place the atoms around the central atom. So 21 pairs to play with. We put the bonding pairs first. 1, 2, 3, 4, 5, then 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? So we have assigned 20 of the 21 pairs, which means that the 21st pair will end up on the central atom, all right? And that would be it. You should calculate the formal charges. I know that the formal charge will be 0, but let's do that anyway. The formal charge for the fluorine, if you remember the formula, it is a group number, which for fluorine is 7, minus half the number of bonding electron, which is 2, minus the number of non-bonding electron, which is 6, so that will be equal to 0. So each of the fluorine atoms will have a formal charge of 0. And we do the same calculation for bromine, which would be 7 minus half of 2, 4, 6, 8, 10, half of 10, minus 2, which would be equal to 7 minus 5, that's 2 minus 2, that's 0, right? So there are no charges present on this molecule, okay? And that's basically how that is done. All right, any questions about this one? Any questions?
I just wrote it 7.
Group number. It's in the group 7 of the periodic table. All right, is it okay for me to clear this?
Really quickly,
Sure.
what does the 2 and the 10 represent? Is that the number of like unbonded things or?
The 10 here represents the number of bonding electrons, and the 2 here represents the number of non-bonding electrons. Let me remind you that the formal charge formula is this. Formal charge is equal to the group number minus the number of non-bonding electrons minus the number of bonding electrons. Right? So in the case of the bromine, the number of non-bonding electrons is 2. And the number of non-bonding electrons is 2, and the number of bonding electrons is 2, 4, 6, 8, 10. So that's where we get the 10 and the 2 here. All right?
So is it always 1/2 of the bonding electron?
Yeah. Okay, any other questions about it? Any other question? All right, so let me clear this and move on to the next. So the sulfate ion. Okay, so let me hear what you have to say about this. What will be the first step?
What number of electrons?
Okay, so sulfur will contribute how many? Six. And each oxygen will contribute how many? Six, but we have to multiply that by 4, right? So that's 24. But we have to take into account the -2. So how do we do that?
And electron.
Right, so we add 2 electrons to that total. So that gives us 32 electrons, which will be equal to 16 pairs. All right. So what's the next step?
Put your sulfur in the middle and
That's surrounded with oxygen, right?
oxygen around it.
Oxygen. Okay, next step. Bonding pairs. So remember now, 16 pairs we have to play with. 1, 2, 3, 4. Then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So what's the next step?
Formal charge.
Formal charges. So let's do the calculation for oxygen. How do we calculate the formal charge of oxygen? I erased the formula. Remember, the formal charge formula is group number minus half the number of bonding electrons minus the number of non-bonding electrons. That's the formal charge formula. All right, so in the case of oxygen, and remember, we're calculating just for one because it's the same calculation for all of it, right? So what's the formal charge calculation for oxygen? 6 minus half of
16.
Nope. 2 bonding electrons. Each oxygen has 2 bonding electrons, all right? Minus the number of non-bonding, which is what? For each oxygen, 6. That is equal to -1. So each oxygen will have a -1 charge. All right? Okay, then we do the same thing for the sulfur. Formal charge of sulfur. What's the group number for sulfur?
6.
6 minus half the number of bonding electrons. How many bonding electrons are there? 8. 8. Right. Minus the number of non-bonding electrons, which is what?
Here.
Okay, so that gives you a grand total of 6 minus 4, which is
It's 2.
plus 2. So the sulfur will have plus 2. Okay, so what do we do from here? We have 4 oxygen atoms, each carrying a negative charge, bonded to the sulfur in the middle, which carries a plus 2 charge. So what do you think is going to happen in this case? We had some situations like this in previous examples we worked the last time. What will happen when you have atoms that are negatively charged bonded to an atom which has plus charges?
I thought you can't do anything because it has 8 valence electrons.
You
So you can't
mean,
add or subtract. You can't add any.
yeah, you can, because remember sulfur is in period 3, and any element from period 3 and beyond can have more than 8 electrons on its outer shell. We just said that. So with that in mind, what do you think is going to happen?
It take one of the electrons from oxygen.
An electron pair from this oxygen here will come and form a bond here, right? So that negative charge will cancel out one of these 2 plus charges. And then for the remaining plus charge, this pair of electrons will come here, and that negative charge will take away that remaining plus charge. So the final answer will be sulfur in the middle, doubly bonded to an oxygen with 2 lone pairs, doubly bonded to another oxygen with 2 lone pairs, singly bonded to this oxygen, which has 3 lone pairs and a negative charge. And the same thing is true for this oxygen, and this will be the final answer. So that would be the Lewis structure for the sulfate ion. Alright? Any questions about this one? Excuse me. Questions?
So would that affect the formal charge at all? Or would the formal charge stay as it is and that only affects the Lewis structure?
Well, we calculated the formal charges at this stage, right? And then we look at the reduction of some of the charges based on negative atoms bonded to positive atoms. So this would be the final answer right here. So you're gonna have, these oxygens will have a formal charge of 0 as a result. And these oxygens will have a formal charge of -2. And by the way, that corresponds to the -2 that we have here in the actual formula for the sulfate ions. So everything basically matches up. All right. Okay, any other question about this? Any other questions? All right. So I take it I can clear this. And let's look at the next one, which is sulfur trioxide. So what do? SO3. Sulfur will contribute how many electrons?
6.
6. Oxygen will contribute how many?
6 times.
6 times 3, which is 18. So 18 and 6 gives you 24 electrons, which is equal to 12 pairs. We put the sulfur in the middle, surrounded with oxygens. And then we put the bonding pairs, right? 1, 2, 3. Then we put the non-bonding pairs around the oxygens. 4, 5, 6, 7, 8, 9, 10, 11, 12. No, what am I saying?
Yeah.
Okay, yeah, all right. So next step is,
Formal charge.
okay, so formal charge for the oxygen would be 6 minus half of 2 minus 6 equal -1. And in the case of sulfur, that would be equal to 6 minus half of 246 minus 0. So that's 6 minus 3, so that's +3. So the sulfur has a +3 charge, and each oxygen has a -1 charge. So what do you think is going to happen in this case?
We're gonna double bonds on
Here,
all of them.
here, and here. So your final answer would be O, double bond S, double bond O, double bond O, and that's it. Yes, sir.
Where do you get the -6 and
Okay, so you mean here and here? These are the number of non-bonding electrons. In the case of oxygen, it has 2, 4, 6 electrons that are non-bonding. In the case of sulfur, there are no non-bonding electrons on the sulfur atom. The sulfur atom has 6 bonding electrons, so that's where this 6 comes from. But it has no non-bonding electrons, so therefore 0 is what we put here. All right. Okay, any other questions about this one? Okay, let's do the last one. Phosphate, PO43 minus. Okay, so phosphorus will contribute how many electrons?
5.
5. And oxygen will contribute how many?
6 times 4.
So that's 24. And then we have to account for the 3 negative charges. So how do we do that?
Add 3 more.
At 3 electrons, right? So that will be 29 plus 3, so that's 32 electrons, which will be equal to 16 pairs. We put the phosphorus in the middle, surrounded with oxygens. And then we put the bonding pairs, 1, 2, 3, 4. Then the non-bonding pairs, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then we do the formal charges. In the case of oxygen, that would be 6 minus half of 2 minus 6, which will equal to -1. And in the case of phosphorus, it's 5 minus half of 8, because there are 8 bonding electrons, minus 0, because there are no non-bonding electrons. So that's 5 minus 4, that's plus 1. So each oxygen will have a -1 charge. And the phosphorus will have a +1 charge. So what's going to happen next? What's going to happen next?
You just have one double bond?
Exactly, because you can shift that pure electron down here, and this plus charge will cancel that negative charge. So you're gonna end up with P double bond O, and then single bond O minus single bond O minus single bond O minus, and that's it. That's going, yeah, it's done. Okay, any questions about this one? Any questions?
In the formal charge equation,
Mm-hmm.
so you're doing 6 minus half of 2 minus 6.
Mm-hmm.
To get,
That's with oxygen,
yeah, to get -1.
right? Because 6 minus 1, half of 2 is 1, right? 6 minus 1 is 5. 5 minus 6 gives you -1. So that will be the formal charge of each oxygen. Right? Okay, any other questions? Any other questions? Any other questions? Alrighty, let's see. Oh, let's look at your assignment. Let me see what's see. Okay, so files. Okay, so based on what we have covered so far, we should now be able to do the first question, right? So you're gonna need that same table, which I alluded to answer this question. The question is asking for you to determine the type of bond based on the difference in their electronegativities between the two atoms involved, right? And then you're going to say, indicate the type of bond by saying whether or not they're non-polar covalent, NPC, polar covalent, PC, or ionic, which is I. So for example, in the case of arsenic and sulfur, I need to show the work here as well. Let me turn on my pen here. All right, so again, I need your help. I need somebody to look up the value for arsenic and sulfur.
2.0 and 2.5.
2.0 and 2.5 respectively.
Correct.
Okay, so the difference would be 2.5 minus 2.0, which would be 0.5. Now remember, the criteria, let me write it up here, is that if the difference in electronegativity is 0.0 to 0.4, then the bond type
Non-polar. Okay.
is nonpolar covalent, NPC, right? If the difference is 0.5 to 1.7, then the bond is considered to be polar covalent. And if the difference is 1.8 to higher, then the bond is considered to be ionic. So 0.5 is within the polar covalent range, so you're gonna put PC there, all right? And that's basically what I want you to do for the rest of it. So I'm gonna leave you just for the minute, give a couple of minutes to work out the rest of them. Which you should be able to do because it's pretty simple.
And these values, like the 2.0 and 2.5, can be found in a table in Canvas?
Yes, if I'm not mistaken, I think it's the very last page, right?
I think so.
Yeah, I think it's the last page in that document. I've read it. Meantime, let's see who came late. Is Chestnut here? Code. Erlinson. Gerard. Here. Green, not here. Kennedy, not here. Leonard is here. Swiss deck. Let me know when you're finished with the first question. So I can we can look at the next question. Together. Are we finished? Or almost finished?
I got no PC at all, so actually no, not no PC, not no non-polar covalent.
Yeah, I don't think there's any non-polar covalent, ones in this. Question. So you're not off, okay, number three, actually, that should have been number two, but I messed up with the number here. It says draw the Lewis dot structure for each compound below. And label each bond as either non-polar covalent, polar covalent, or ionic. So in the case of water, that's pretty easy if you go through the steps that we described earlier. Hydrogen will contribute, hydrogen will contribute 1 times 2, oxygen will contribute 6. So that will give a grand total of 8 electrons. So the oxygen would be in the middle. Now, in this case, let me just say, in the case of water, it turns out that the more electronegative element will be in the middle. And the only reason why that is so is because that's the only possible arrangement. Because remember, hydrogen cannot have more than 2 pairs of electrons, or well, no more than 2 electrons on its outer shell. So therefore, you must have the oxygen in the middle and the hydrogen surrounding it like this. We have 8 electrons, which is equal to 4 pairs to play with. So we put 1 pair here, 1 pair here, and then the remaining 2 pairs cannot go on the hydrogens, but will go on the oxygen. So that would be the Lewis structure for water. And then we have to tell what kind of bond this is. So of course, we have to go to the table and look up the values for oxygen. Can somebody tell me what that is?
3.5,
3.5, and hydrogen is
2.1.
2.1.
Yes, sir.
So the difference between those two would be 2 and 1.4, right? So where does that put that type of bond? It would be what? Polar covalent. So therefore, these bonds would be polar covalent, right? In the case of sodium chloride, well, basically sodium chloride will have ionic bond because the sodium chloride consists of ions, Na plus and Cl minus. This will be the Lewis symbols, right? And if you look at the values, what's the value for sodium?
0.9,
0.9, and the value for chlorine is what?
30.
30. So the difference between those two will give you 2.1, which would be obviously greater than 1.8. So therefore, this would be ionic. Yes, sir.
So for that, what did you write? You just did the Na, the Cl with oxygen.
Right, exactly. The chlorine will have the 8 electrons on its outer shell, and the sodium will simply have, well, sodium had 1 electron on the outer shell, which it gave up to the chlorine, right? So therefore, we represent the sodium like this, and the chloride like that, and that's it. And it's ionic. Okay, in the case of carbon, carbon will contribute 4, oxygen will contribute 6 times 2, so that's 10. So that gives a grand total, I'm sorry, 12. That gives a grand total of 16 electrons, which is equal to 8 pairs. We put the carbon in the middle, surrounded with oxygens. We put the bonding pairs first. 1, 2, 3, 4, 5, 6, 7, 8. Then what do we do next?
The 3.5 minus 2.5, 51 point.
Well, let's complete this first, the Lewis structure. If you calculate the formal charges, you'll see that oxygen will have a formal charge of -1, and carbon will have a formal charge of +2. So this will be -1, this will be -1, this will be +2. So this will go here, this will go here, and the Lewis structure of carbon dioxide is. And as you were alluding to, carbon, what's the electronegativity value for carbon?
2.5,
2.5, and for oxygen, it's what?
3.5.
3.5. So the difference obviously will be 1.0, which will place these bonds in what category?
Polar covalent.
Polar covalent, right? And then finally, in the case of NF3, nitrogen will contribute 5, each fluorine will contribute 7 times 3, so that's 21. So that gives you a grand total of 26 electrons, which will be equal to 13 pairs. Let me erase some of this here. Get some space. So, we put the nitrogen in the middle, surrounded with the fluorines. Put the bonding pairs first. 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12, which means that the 13th electron will go here. And well, the formal charges will be 0. You can calculate that and you'll see 0. So let's look at what type of bond it is. What's the, well, I know fluorine is 4.0. What's the value for nitrogen?
3.0.
3.0. So the difference is 1.0. So again, these will be polar covalent bonds. Right? And that's what you do. Okay, any question about this? Any question? Questions? Okay, let me clear this. Clear all of this. Let's see if we can do the next question. Oh, we can do that. Yeah, okay, so let me go back to the PowerPoint and see if I can at least touch this topic of resonance. And let me just say that resonance is a very important topic, especially for those of you who plan to do organic chemistry. What you're going to see is that this whole idea of resonance is used to explain a lot of things that are observed, reaction products, why one product is formed over another, or why reactant, or why one organic compound reacts faster than another. So we won't get into all that. I'm just going to talk about what this theory is all about. And basically what this resonance theory says, excuse me, is that if you have a molecule or ion that can be legitimately represented by two or more Lewis structures, where the difference between them would be the distribution of electrons, then those separate structures would not by themselves represent the true structure of that particular molecule or ion. Instead, according to this theory, the real structure is a hybrid between those different structures, all right? So here's an example, the ozone molecule. If you were to follow all the steps that we just did for determining the Lewis structure for different substances that we did in the past, if we do those same steps for ozone, you're going to end up with either this structure or this structure, right? So for the sake of making things clear, what I'm going to do is I'm going to number this 1, this oxygen atom 1, this 2, and this is 3. And I'm going to maintain that order here, right? Even though the oxygen atoms themselves are identical in reality, but just to explain what's happening here, I'm just going to distinguish between them by using that numbering system, right? So this oxygen number 1 is the same as this oxygen number 1, and so on for 2 and 3, all right? So basically, you'll notice that the difference between, there are a couple of differences actually. One difference between this structure and this structure is that there is a single bond between carbon 1 and between oxygens 1 and 2, and there is a double bond between oxygen 1 and 2 here, right? And in this case here, there is a double bond between oxygens 2 and 3, and a single bond between oxygen 2 and 3. Not only that, there's also a difference in electron pairs, lone pairs of electrons and bonding pairs. So in the case of the oxygen here, number 1, it has 3 lone pairs, but that same oxygen here would have 2 lone pairs. And the reverse is true for this oxygen, right? Oxygen number 3. In the case of oxygen number 2, it still has a lone pair here and here, right? So those are some differences that you can identify between those two structures. So what the resonance theory says is that neither this structure or this structure represents the true structure of ozone. Instead, the true structure of ozone is a hybrid of those structures. And I remember when I was a student, I had some difficulty, appreciating what is being said here until I don't remember where I saw this, but there's a biology example of hybrids, or there's several biological examples of hybrids. And the one I remember being that I used to understand this is the relationship between a horse, a donkey, and a mule, right? The mule is a hybrid between a horse and a donkey, right? So what that means is that the mule will have some characteristics in common with the horse, and other characteristics in common with donkey, right? But the mule is not a horse or a donkey, all right? So basically, it's the same idea here. The real structure is a hybrid of those two structures, right? So basically, looking at one structure or the other does not give you the true picture for the ozone molecule. And in fact, there's some information data that shows that the hybrid is, kind of like a mix between the two. For example, one would expect that in this structure here, this bond length would be shorter compared to this bond length, right? That's what you'd expect because typically double bonds have a shorter bond length compared to single bonds, everything else being the same, right? So that's what you'd expect based on these structures. What actually happens when people went through the trouble of measuring the bond lengths, they found out that the bond lengths are the same, right? And not only that, they found out that the bond lengths are somewhere in between that you'd expect for a single bond and that you'd expect for a double bond. So it's somewhere in between, right? So that just goes to show that the real structure has some characteristics with the resonance structures, but it's not quite the same. It's a hybrid, all right? So that's basically what all of this is saying here. The different structures are called resonance structures, and the real structure is said to be a hybrid, a resonance hybrid of those structures, all right? So applying that to this example, it says, write 3 equivalent Lewis structures for the carbonate molecule, where this should be ion, that conform to the octet rule and describe how the resonance hybrid is related to this 3 structures. So I'm just going to draw one Lewis structure of the carbonate here, and I'm going to show you how we get the other Lewis structures. All right, so this is one. So what we can do is push this pair of electrons here to form a double one, and at the same time, this pair of electrons will move over there. So the resulting hybrid structure for that movement of electron pairs would be this, right? And then this goes here. No, I'm sorry. Not that. This goes here, and this pair of electron goes here, and you're going to end up with O, single bond, C, O, double bond, O, and minus charge here, right? And those are the 3 resonance structures for the carbonate ion, all right? And let me see here. Oh, I forgot to mention, whenever you see the symbol here, an arrow with 2 heads, that basically is indicating that the relationship between the structures on either side are resonance structures, all right? And let's show the questions. It says, describe how the resonance hybrid is related to the, well, like I said, the hybrid will have characteristics of each of these, right? And in fact, in some textbooks, what they will do is show you what the hybrid, a diagram which shows you what the hybrid looks like. And let me just show you what we're talking about here. And then you have this is a dotted line. All right. So basically, you'll notice that the negative charges basically are moving as you go from one resonance structure to the other, right? So basically, what that indicates is that the charge is being spread among the 3 oxygen atoms, and we represent that by using the same partial charge symbol, delta minus. What that indicates is that the charge is delocalized. That's the term that is used, which is going to be very important, as I said before, when you get to organic chemistry. For those of you who have to do organic chemistry, this will become important, especially when you get to the discussion of aromatic compounds and some compounds that are not aromatic. All right, so that's basically how we deal with this question right here. All right, what time is it?
38.
Okay, let me see if I can go through this quickly. Let's talk about this term bond order and what it relates to bond length. Bond order is very simple. It's the number of electron pairs that are shared in a bond between 2 atoms. So therefore, a single bond will have a bond order of 1, a double bond will have a bond order of 2, and so on, right? The bond length is the distance between the two nuclei that are joined by a covalent bond. And we have some examples of different molecules where the bond lengths are given, they're given in picometers. Remember, 1 picometer is 10 to the minus 12 meters. And there's a relationship that exists between bond length and bond order, all right? Typically, let me just tell you that now. Basically, everything else means the same. The greater the bond order, the shorter the bond length. We're going to see some examples of that later on. But before we do that, let's talk about the bond dissociation energy, which is the energy required to break 1 mole of a particular type of covalent bond in a gas-phase compound, right? So if you take, for example, the hydrogen to hydrogen bond, it takes this much energy to break that bond, all right? In the case of the water molecule, you have 2 oxygen to hydrogen bonds, and it turns out that it takes this amount of energy to break 1 bond first, and then to break the other bond, it takes this amount of energy. All right? So basically, as you can see, for the OH bond, it depends on which one is broken first in the case of water molecules, right? And also for other molecules which contain the OH bonds, their values will be slightly different, right? So therefore, what was done was that people have compiled data where they determined the average bond energy that would exist to break a bond between 2 atoms. And the table looks something like this, right? So these are basically all the average bond energy listed here and the corresponding bond lengths listed here, all right? And based on the data that you see here, we can see certain patterns in terms of the relationship between the bond order and the bond dissociation energy. So for example, if we take these 3 right here, right? Carbon to carbon, single, double, and triple bond, right? What you'll find is that the bond length decreases, right? As you go from single to double to triple, right? So the greater the multiplicity of the bond, the closer will be the atoms to each other, and therefore the bond distance will decrease. We also notice among those 3 types of bonds that the bond dissociation energy increases, all right? And that is true right across the board. If you look at these 3 right here, different atoms, but same type of multiplicity, the bond length decreases with increasing multiplicity of the bond, and the bond energy increases with increasing multiplicity of the bond, all right? We see the same trend here. We see the same trend here between carbon and oxygen. We see the same trend here between nitrogen and oxygen. We see the same trend here between oxygen, and so on and so forth, all right? So that's one trend that we observe. Another trend that we observe is that if one atom of the bond is fixed and the other one changes, we see that the bond distance increases with the increasing size of the atom, all right? So an example of that would be right here, right? We have carbon bonded to hydrogen, nitrogen bonded to hydrogen, and oxygen bonded to hydrogen, right? So in terms of the atomic size increases this way. Oops, sorry, increases this way, right? Oxygen is smaller compared to nitrogen, compared to carbon. And look at the corresponding bond lengths. There's an increase in the bond length as well. As you go from HO to HN to CAC, the bond length increases accordingly. And also, now the thing about the size of the atom as it relates to the bond energy, there's not that great a correlation, right? So I'm not sure we have an understanding to explain why that's observed. As you can see here, it for oxygen to hydrogen, it's 464, and then it drops to 489, sorry, 389 for nitrogen to hydrogen, and then increases to 414 for carbon and nitrogen. I'm not sure the reason why that happened, right? So those are just some trends that you'll observe. Okay, so I mentioned that trend, and yeah, so that's the trend in terms of the multiplicity of the bond. All right. Okay, I don't think we can cover this. In today's class, so I'm just going to complete that next class. But before you leave, just to let you know what's going to happen for the rest of the term. So your next test, I think I made an announcement about that in campus. Let me just check and make sure.
Yeah.
Oh, okay. Yeah, sometimes I do these things like on the fly and I remember. So just to remind you of the dates. So your test number 3 will be next week. Sure. Okay, yeah, next week Tuesday. And what I plan to do is, I didn't mention it here, but I was thinking that for the purposes of review, we could meet, hold on, so. Oh, and the final exam is on the eighth, all right? So I was thinking that we could review for the final, if you want to.
Absolutely.
Okay. I was thinking on Thursday, the first. And I was thinking that we could just do it online unless you definitely want me to meet in person. But I was thinking that we could make it a Zoom class, since that would be, well, because class is actually end. When is the end of semester? Is it the 30th? Let me see here.
Thought it was after.
No, I mean, end of classes, that's what I meant to say, end of class, where would that, academics?
So the review would be over Zoom.
Okay, let me just check something here. Okay, it says your classes end on May 2nd. Oh, so we should still be attending class anyway, so we can use that for review purposes. So I propose that we meet on Thursday to review. I suggest by Zoom, unless you definitely want me to, if you definitely want me to be here or to do it in person, let me know, right? But I'm planning to do it by Zoom, all right? So, that's basically the purpose of that class. Let me remind you that the final exam will be comprehensive. I'm going to try to make it a question per chapter. And, I think that's it. All right,
So if class is in the first,
the class,
and
according,
it's the
the
final,
last day of class is the second.
so is the final gonna be online then?
No, the final would be, in person on, what day did I say?
The eighth.
The eighth, which will be the Thursday following. So we meet here at the regular class time. And the exam will be 2 hours. Which reminds me, yes, yeah, okay, yeah, so that's it. I have to figure out what happened to the intro there.
We won't have class at 6.
Hmm?
Correct, that Tuesday.
No, because that's exam week, no classes. All right, folks, so for those of you out there in Zoom, I'm gonna sign off now. Yes, sir.
Is there a lab today?
Yeah, well, it depends. Some students didn't finish their,
Oh, there's spirit.
yeah, so but if you finish last week, that's it.